My name is Chris and I also work at the UK Centre for Ecology and Hydrology, and I'm based out of what is today a rather windy Scotland. So just to summarise our digital twin a bit, this wire diagram shows the connected elements of our digital twin. Please don't worry about trying to memorise the content. I really just wanted to highlight that it's made up of two ecosystem service models. I'm going to cover the recreational potential model part now, which is highlighted in red on the diagram. And then Simon's going to talk a bit about the biodiversity model. So as biodiversity is particularly relevant to the cultural ecosystem services, what we have done was to adapt an existing recreational potential model whose parameterization captured elements of at least 4 recognized cultural ecosystem service classes, including for the biotic and abiotic cultural services. The aim was then to integrate this with biodiversity. So the 4 recognized ecosystem service categories the model is currently parameterized for are active and immersive interactions. So in this example image, hiking in the mountains and what is fairly unpleasant weather. And then for passive or observational interactions, so for example, wildlife experiences and visiting different habitat types. And then abiotic characteristics of nature that enable active or passive physical and experiential interactions. A good example of this can be rivers and streams. And then finally, we've got the abiotic characteristics of nature that enable intellectual interactions. And in this example, we were discussing long-term scientific monitoring within a nature reserve. Put simply, the recreational potential model is a multiple lookup model, which outputs as a raster map with a recreational potential value for each pixel. Basically, this just means it just adds together values from multiple input data sets and then displays that in a single output. The first stage is to agree on and define the geospatial input data sets which make up each model component. I'll be coming back to the model components shortly. A user then would score the features in each input on its suitability to provide opportunities for outdoor recreation, and they'd score that on a 0 to 10 scale. A user could be an individual or an expert working with recreational user types, or a predetermined persona. At this moment in the development, we're only using this persona approach for simplicity reasons. Currently have 2 personas parameterized, but I'll move on to that shortly as well. There are also some features which are known to have a disproportionately strong draw to recreationalists. And this is things like path networks or water, such as rivers and lakes. To represent these features, we also give them a proximity value that goes down as the distance from that feature would increase. The inputs and components are eventually normalized and summed to provide this single mappable pixel value between 0 and 1. So to give an idea of how that scoring works, this table contains information on a digital elevation model of slope. And the angles were grouped into several steepness categories. These were then scored for their recreational opportunity by 2 persona recreational types. Firstly, a soft recreationalist, which is somebody who might do, say, short trips over fairly easy terrain or on maintained trails. And then also for a hard recreationalist, which is maybe a climber or a mountaineer who's drawn to more difficult or remote terrain. As you can imagine, a soft recreationalist sees greater opportunity in easier slopes and ultimately scores these as being greater recreational opportunity than, say, the hard recreationalist did. Ultimately, we would love to make this parameterization available at the individual user level rather than a persona to give a truly personalized output. That means a user could then use a tool to identify areas which are particularly suited to their own recreational needs. So I mentioned the model has 4 main components, each of which utilizes multiple available geospatial data sets. The first part is the suitability of land to support recreational activities. This is essentially a measure of the degree of naturalness, and we parameterize this with things like land cover maps and areas of high natural value farming and things like that. The second component is features that influence the potential capacity to provide recreational opportunity. Now, this is split into 2 parts: natural features and infrastructure features. The natural features could be a digital elevation model, as I've just shown you, of the terrain, or geological formations, or maybe vegetation classifications. The infrastructure features influencing the potential provision could be access points or path networks. And then finally, the last component is water. The proximity to water, be it lakes or rivers, has been shown to be especially important for recreation. So this is captured separately from other features. This is just 2 example outputs for the soft and hard recreationalist. You'll see, not unexpectedly, that the hard recreation places more value, which is darker green on areas on the map, on the central high plateau of the Cairngorms, and also in other remoter areas. Soft recreationalist puts more value on accessible valley bottoms and riparian areas, which you can see more around the perimeter. So the pDT was focused on the Cairngorm National Park, but we're already thinking about how we upscale this to the whole of Scotland, or potentially even further afield. This has its challenges, particularly in relation to input data and things like computational resources. For example, with the input data, you need to consider whether specific data sets are available at the scales you need. Several of our Cairngorm data sets were specific to that area. So we need to think about analogous data sets that might cover the entire region of interest or the whole of Scotland. You might also have highly specific data sets or features of data sets, which can be important for specific recreational potential in your local area, but also doesn't apply to larger areas. For example, in a small area, you could score a river's potential for recreation by, say, its name and through local knowledge of its characteristics. But when you try and upscale the model to larger areas, which may contain many rivers, this becomes entirely impractical. So a different set of more generic scoring criteria are required. For example, you might score rivers only by their size. This is an example of a reduction of fidelity. Now, fidelity is quite tricky to summarize, maybe, but it's probably best described as a measure of the realism of the model, or how well the model matches the real world. Basically, the more you zoom out, the less you see. And I think that takes me to the end.